So we're starting section 5.1, area and distance. So first thing, the area problem, then the distance problem, and then summation notation. So area measures the size of a two-dimensional shape. Area is preserved under cutting, gluing, sliding, rotating, and so on. Area measures in the standard formulas of the area that we know of are the common ones. The area of rectangle is side times side. Triangle is side times height divided by 2. Circle is pi times radius to the power 2. But what if we have a complicated shape? What do we do with that? So the motivation for this chapter is the problem of calculating the area of a more general region. And this is area of a, like, for example, area under a graph of a function in y equal to f of x, and or other curves, and so on and so forth. When we're discussing the tangent line, we very quickly discovered that we need limits to calculate derivatives and slope of the tangent line mathematically in a rigorous way, and this started the derivative, and then when we're trying to find the area, we realize that we need again limits to be able to calculate the area in a rigorous way, and this leads to the concept integral. So look at the area of the region bounded for a function f of x that is continuous and positive on a closed interval a and b. Look at the area of the region bounded by the graph, and x equal to a, x equal to b, and x-axis. And so how do I compute this? And what we do is we start with approximation of the area. Approximation with what we know the best, area of the rectangle. And so we divide the area that we know into pieces. We divide the area by dividing the x-axis between a and b into n little line segments, and that means that each one of these the new line segments are going to be of the length b minus a divided by n, and we call that delta x. And so here is the division, and then we choose sample points in each interval. Using those sample points, we find a height, and the height is how we plug in the sample point in the function to find the height. So the rectangles are going to be sitting on the function basically, and so in this way we divide the line segment A to B into pieces, and we build on the rectangles above it, and the rectangles all together add up to the area of the add up to a good estimation of the area of the under the graph of the function. And so what if we try this, and so notice again, the height is going to be f of some xi, and the width of each rectangle is going to be delta x. And so I write down the area is estimated by f of x1 times delta x plus f of x2 times delta x, all the way to f of xn times delta x. Now let's approximate the area under y equal to x squared on 1 and 4 using 6 line segments. First step, divide. 4 minus 1 divided by 6 is going to be into 6 line segments of the length half a unit. And so you start from, basically, you start from 1, you add half, you get 1.5, that's the first interval. Then from there, 1.5 plus, you add another half and you get 2, and all the way to the 6th line segment. And then graphically, if you do that, you get these 6 line segments, and you have different approaches to choose xi. One way is to choose right endpoint. If you're choosing the right endpoint, then you're choosing points that are basically either you're choosing 1, then you're choosing 1.5 for that interval. Then no, the right endpoint is the other way around, isn't it? The right endpoint for this interval is going to be 1.5, then 2 for that one, then 2.5, then 3, then 3.5, and 4. And so this rectangle is going to be the width, which is 0.5 times 1.5. Then the next one is going to be times f of 1.1. F of 1.1, f is x squared. So you start with the first interval. The xi is the right one. That's 1.5. F of xy is 1.5 to power 2, which is mentioned right there. And then the second one is the second interval ends at 2, and then f of xi for that is 4, and then the third one ends at 2.5, and the third one ends at 2.5, and the f for that one is 2.5 to power 2, and so on and so forth. And this is how you find every rectangle, area of every rectangle. So finding all these f of xi's and multiplying it by delta x, you get all the areas of the little rectangles. You add them all together, you get the area of the entire all the additions, and it gives you that estimated area that you see over there. Now what do we do if we have left endpoints? Again, breaking the interval into pieces is the same. You have the 6 intervals, and each one is 0.5. This time around, when you're trying to find the height of the rectangle, you use the left endpoint, and that is over here, left endpoint, and that's f of left endpoint here is f of 1, which is 1. Over here, left endpoint, it's 1.5 to power 2. Here, left endpoint is 2 to power 2, and so on and so forth. And you get the you get all these areas of the rectangles. You add them together, and using the left endpoint sample, you approximate the area under the y equal to x squared. Now, what about the midpoint? What is a midpoint? Look at each interval. The first interval is 1 and 1.5. So the midpoint for that one is going to be 1.25. The second one, the midpoint, is going to be 1.75. Now you see the pattern, you just, because midpoints are going to be 0.5 away from each other, and this one is 2.25, this one is 2.75, and so on and so forth. You plug those points in the function to find the height of the rectangle this time, rather than putting one of the endpoints, and then you find the height, the area of each rectangle, and you add them all up together to get the answer for this. Now, using all the three estimation, right endpoint, left endpoint, and midpoint, you can look at the differences. You see the different colors are representative of the different endpoint estimation. You see the light pink is over and light green is under, and it seems that in this case the purplish color is the closest. That's the basically the midpoint, and it doesn't mean that it's all. So let's talk about expressing area as a limit. We've seen all those rectangles, and sometimes one rectangle works better than the other one. Now we want to approximate the area by basically adding those areas of the rectangles. This is called the Riemman sum of n, and you see their n rectangles are sub n. And so as n gets larger and larger, that means that you decrease the size of delta x, you decrease the width of all those rectangles, the approximation gets better and better. So let's watch it over here. N equal to 5, you can see there are pieces that are above and below, and I don't know what's going on, as it's close enough. And then when you make the n equal to 10, those pieces are smaller. Whatever is above and below is smaller, and then smaller and smaller and smaller and smaller. And at n equal to 30, it's pretty good approximation. It's just a little bit over and under. And so this is how we talk about limit. If you remember, with the slope of the secant line, we were getting the 2 points closer and closer, and we ended up with the slope of tangent line. Here with approximation, we make the width smaller and smaller, and the approximation gets better and better when we increase the number of the rectangles. So the exact area is actually given by a limit of the Riemman sums. The area A under the graph of a continuous function f between x equal to a and x equal to b equals the limit of the sum of the areas approximating rectangles, and so a is equal to limit as n goes to infinity of r sub n, or limit as n goes to infinity of f of x1 delta x plus f of x2 delta x plus all the way f of x and delta f of x and delta x, and that sum is called the Riemman sum. Now let's remember the calculating